More than 25 billion kilometers from where you are standing, a small machine built in the 1970s is still whispering back. What it found at the edge of the sun's reach is not what anyone expected. There is a wall out there. It is invisible, it is silent, and it is on fire in a way that fire was never meant to be. Tonight, we will travel outward from the sun, through every invisible layer of the solar system's edge, and arrive at last at the interstellar ocean no human eye has ever seen, understanding why a single faint hum heard by a nearly 50-year-old machine may be one of the most profound sounds ever recorded by our species. Before we dive in, if you love exploring the outer edges of our universe as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a version of this story that almost everyone knows, and it goes something like this. The sun sits at the center of a system of planets. Beyond the farthest planet, space begins, a vast, empty darkness through which Voyager 1 has been sailing since its launch in 1977. Eventually, it crossed the edge of the solar system and entered interstellar space. The end. This is a tidy story. It has the feel of a completed thing, a project with a known outcome and a satisfying conclusion. It is also, in almost every significant detail, incomplete. And the places where it breaks down are precisely the places where the universe reveals something extraordinary about itself. The textbook answer begins to fall apart the moment you ask a deceptively simple question. Where, exactly, does the solar system end? Most people will say it ends at Pluto, or perhaps just beyond Pluto, where the planets run out and the darkness takes over. That picture is almost entirely wrong, and recognizing why it's wrong opens up a much more complicated and deeply beautiful geography. A set of nested boundaries, each one stranger than the last, each one revealing a hidden truth about the relationship between our sun and the galaxy that surrounds it. So take a moment to settle in. What follows is a journey outward, not in the sense of a simple straight line from here to there, but in the sense of a gradual revelation, a peeling back of layers that most people never knew existed. We will begin close to the sun, in territory that feels almost familiar, and we will move outward, step by step, through a progressively stranger country until we arrive at the place where Voyager 1 now drifts, surrounded by the ancient, cold, turbulent gas of interstellar space. And along the way, we will encounter a series of boundaries, a shockwave, a dead zone, a wall, each one a place where the simple story collapses and something richer takes its place. To understand what Voyager found, you first need to understand what it was moving through. The sun does not simply sit quietly at the center of the solar system, bathing the planets in light and warmth. It breathes. Every second of every day, the sun exhales an enormous stream of charged particles, mostly protons and electrons, moving outward in all directions at somewhere between 400 and 800 kilometers per second. This outflow is called the solar wind, and it does not stop at Neptune or Pluto or any other convenient boundary. It keeps going, far beyond the planets, pushing outward into space, carving out a vast bubble in the surrounding medium of gas and dust and magnetic fields that fills the galaxy. That bubble is called the heliosphere, from helios, the Greek word for the sun, and it is the true extent of the sun's direct physical influence in the cosmos. The heliosphere is not a fixed thing with sharp edges, like a soap bubble frozen in time. It is dynamic and irregular, shaped by the pressure of the solar wind from within, and by the pressure of the interstellar medium from without. It breathes in rhythm with the sun's own cycles, swelling slightly during periods of heightened solar activity, contracting when the sun is quieter. On its sunward side, the boundary is pushed closer. On the side facing away from the direction of the sun's motion through the galaxy, it stretches out into an elongated tail, like the wake behind a ship. Voyager 1 and its twin are now outside this protective bubble of particles and magnetic fields generated by the sun. The solar wind is not simply moving outward into empty space when it leaves the sun. It is moving into a region already occupied. The interstellar medium, the gas and dust and magnetic fields that fill the space between stars, is itself not empty. It is a thin, cold, slow-moving medium, and the outward rushing solar wind must eventually push against it. The contest between these two forces, the outward pressure of the sun's wind and the inward pressure of the surrounding galaxy, defines the outer structure of the heliosphere, and it produces, at several distinct distances from the sun, a series of remarkable physical boundaries. These are the boundaries Voyager 1 has been crossing, one by one, over the course of nearly half a century of travel. And each crossing, when it finally happened, turned out to be full of surprises. The first boundary is called the termination shock. To understand it, picture the solar wind moving outward at hundreds of kilometers per second. At some point, roughly 80 to 100 astronomical units from the sun, where 1 astronomical unit is the average distance from the Earth to the sun, about 150 million kilometers. The wind runs into a region where the pressure of the surrounding interstellar medium begins to assert itself, and the wind can no longer maintain its supersonic speed. The technical term is important here: supersonic. The solar wind in the inner heliosphere is moving faster than the speed of sound in the plasma, the equivalent of a supersonic aircraft breaking the sound barrier. When the wind slows enough to drop below this threshold, it does so abruptly in the form of a standing shock wave. This is the termination shock, the place where the sun's outrushing wind hits its speed limit and transitions, abruptly and violently in physical terms, into a slower, hotter, more turbulent region beyond. Voyager 1 crossed this termination shock of the supersonic solar wind on December 16, 2004, at a distance of 94.01 astronomical units from the sun, becoming the first spacecraft to begin exploring the region beyond it. This crossing had been anticipated for years. Scientists had modeled the termination shock extensively, built theories about what the solar wind would do when it slowed, and made predictions about what the particle environment would look like on the other side. What actually happened was both confirming and confounding in ways that nobody had fully anticipated. One of the people studying those results most carefully was Edward Stone, a physicist at the California Institute of Technology in Pasadena, who had been the chief scientist of the Voyager mission since its inception. Stone had spent decades patiently tracking Voyager's progress, waiting for the termination shock crossing, and in 2005, he published his analysis of what the spacecraft had found. In contradiction to many predictions, the intensity of anomalous cosmic ray helium did not peak at the shock, indicating that the source of these anomalous cosmic rays was not in the shock region local to Voyager 1. This was unexpected. The prevailing theory had been that anomalous cosmic rays, a particular class of energetic particles, were accelerated at the termination shock and peaked in intensity right there, at that boundary. Instead, the particles kept increasing in the region beyond. Something else was going on in the space between the termination shock and the next boundary outward, the one called the heliopause. That space, the turbulent, compressed region between the termination shock and the heliopause, has a name. It is called the heliosheath. The heliosheath is one of the least discussed but most physically interesting regions of the outer solar system. Imagine a thick, irregular shell surrounding the entire heliosphere, filled with the slowed down, heated up, turbulent remains of the solar wind after it has been compressed and redirected by the termination shock. The solar wind enters the termination shock, moving at hundreds of kilometers per second, and emerges on the other side, moving at a fraction of that speed, hotter, denser, and pushed sideways and backward by the pressure of the surrounding medium. In the heliosheath, the smooth radial outflow of the inner solar system gives way to something more like the churning surface of a slow river, complex, braided, full of eddies. Voyager 1 spent roughly 8 years traveling through the heliosheath after its 2004 termination shock crossing. During those years, it was taking continuous measurements of the particle environment, the magnetic field, and the plasma waves around it. The data it sent back revealed a heliosheath that was more complicated and in some ways more puzzling than models had predicted. There were layers within layers, regions where the particle counts changed abruptly, regions where the magnetic field shifted in unexpected ways. The closer Voyager 1 got to the heliopause, the stranger things became. Stamatios Krimigis, a physicist at the Johns Hopkins University Applied Physics Laboratory, was among those watching these measurements closely. In 2011, he and his colleagues published a finding that genuinely surprised the community. In a region close to the anticipated heliopause, Voyager 1's instruments were registering essentially zero outward flow velocity for the hot plasma around it. The solar wind, which had been moving outward through the entire history of the spacecraft's journey, had, at least locally, stopped moving outward. It was, in a sense, stalled. Before the communications interruption in late 2023, Voyager 1 had been traversing a mysterious new region of interstellar space, perhaps an enormous swell of pressure or a cloud of ancient plasma, and scientists were eager to resume the investigation. This was one of those moments when the data simply refused to match the models, and a choice had to be made. Was the model wrong, or was the interpretation of the data incomplete? In the years that followed, as more data came in and the community debated the implications, the picture only grew more nuanced. Voyager 1 was approaching a boundary unlike anything it had yet encountered, and the question of what that boundary would actually look like, on the instrument level, in the actual measurements a 40-year-old spacecraft would be capable of making, was still deeply uncertain. Something here deserves attention, because this uncertainty is not a failure of science. It is exactly what science looks like at the frontier. The heliosphere is the only stellar bubble of this kind that humanity has ever explored directly, from the inside out, with a physical probe. Everything that was known about heliopauses before Voyager 1 reached one was inferred from theory, from indirect measurements, from models built on solar wind observations taken much closer to the sun. When a probe actually reaches the thing you have been modeling, it very often turns out that the model was correct in its broad strokes and wrong in its fine details. And the fine details, it turns out, are where the most interesting physics lives. Voyager 1 was about to encounter, in the most literal sense, the last thing standing between the sun's domain and the open galaxy. And what it found there would eventually force scientists to rewrite, in several important respects, their understanding of what a stellar boundary actually is. Take stock of where we are. We have moved outward from the sun to a distance of roughly 120 astronomical units, about 18 billion kilometers. We have crossed the termination shock, the standing wave where the sun's wind breaks down from supersonic to subsonic. We have moved through the heliosheath, the thick, turbulent, slowed wind region beyond. And now, ahead of Voyager 1, lies the heliopause itself, the boundary that separates the solar wind entirely from the interstellar medium, the true outer edge of the Sun's direct physical domain, the place where one kind of space ends and another begins. The intuitive version of what the heliopause looks like is a sharp, clean surface, a wall, if you will, on one side of which is the Sun's material, and on the other side of which is the galaxy's material, and the two never mix. This is a useful approximation, but like most intuitive versions of complex physical boundaries, it doesn't survive contact with real data. Scientists have had to highlight the importance of magnetic reconnection at the heliopause, one of the key processes driving the interaction between solar and interstellar media, and debate the observations that have shaped the current understanding of the heliopause's definition, location, and shape. The real boundary is more like a coast than a wall. Coasts are places where two fluid domains, land and sea, meet and interact, erode and deposit, in a complex and constantly shifting zone. The heliopause is a place where two plasma domains, the solar wind and the interstellar medium, meet and interact, with magnetic fields from both sides pushing against and threading through each other, with occasional eruptions from the Sun, what are called coronal mass ejections, or CMEs, sending shocks through the heliosheath that arrive at the heliopause and push against it from within. The boundary fluctuates. It moves. It is not a line in space. It is a region, a transition zone, and Voyager 1 apparently crossed it, and then recrossed it several times in a period of weeks before settling, definitively, on the outside. August 25th, 2012. That is the date that NASA eventually settled on as the moment Voyager 1 crossed the heliopause and entered interstellar space. A key finding that persuaded many scientists that the heliopause had been crossed was an indirect measurement of a roughly 40-fold increase in electron density, based on the frequency of plasma oscillations observed beginning on April 9, 2013, triggered by a solar event. But the confirmation did not come immediately. The crossing itself was ambiguous in real time because the instrument that would have most directly measured the change in plasma environment, the plasma spectrometer, had stopped working in 1980. Without it, the team had to piece together the evidence from the instruments that were still functioning: the magnetometer, the cosmic ray instrument, the plasma wave subsystem. Each one told a partial story, and the complete picture only emerged over months of careful analysis. The possibility of observing the interstellar plasma using the plasma wave instrument only occurs episodically, when energetic electron beams excite local plasma oscillations in the interstellar plasma. If those oscillations are not excited, there is no way to measure the local plasma density on Voyager 1. This meant that the team had to wait, not for Voyager to cross the boundary, but for a specific physical event to occur that would illuminate the plasma around it, like shining a flashlight into a dark room and waiting to see what the light revealed. That event finally came on April 9th, 2013, when a surge of electrons associated with a solar eruption propagated outward through the heliosphere, reached the heliopause, and triggered a distinctive oscillation in the surrounding plasma. The frequency of that oscillation is directly related to the density of the electrons in the plasma, a technique that is well understood in plasma physics and is sometimes compared to ringing a tuning fork near a wine glass and listening to the note to determine the glass's composition. On that date, the Voyager 1 plasma wave instrument began detecting locally generated electron plasma oscillations at a frequency of about 2.6 kHz. This oscillation frequency corresponded to an electron density of about 0.08 per cubic centimeter, very close to the value expected in the interstellar medium. These and other observations provided strong evidence that Voyager 1 had crossed the heliopause into the nearby interstellar plasma. The scientist who made this measurement and published its interpretation was Donald Gannett, a plasma physicist at the University of Iowa, who had been involved with the Voyager plasma wave instrument since the mission's beginning in the 1970s. In 2013, Gannett and his colleagues published their analysis in the journal Science, announcing to the world that Voyager 1 had, definitively, entered interstellar space. The announcement was met with genuine excitement from the scientific community and from the public. Here was a machine built by human hands, launched in the same year that Star Wars opened in theaters, that had traveled so far and for so long that it had exited the sun's domain entirely and was now sailing through the space between the stars. It was a milestone. It was extraordinary. And it was, as it turned out, only the beginning of what Voyager 1 would find in the years that followed. The heliopause crossing in 2012 was the end of one chapter and the beginning of another. Crossing the boundary was the milestone the mission had been building toward for 35 years. But milestones are not destinations. They are places where you pause, take your bearings, and realize how much of the territory ahead remains unmapped. What lay beyond the heliopause was called the very local interstellar medium, a term that sounds almost modest, given what it actually refers to. The very local interstellar medium, abbreviated by scientists as the VLISM, is the region of galactic space immediately surrounding our heliosphere, the ancient plasma and gas and magnetic fields of the galaxy that press against the sun's bubble from the outside. It is material that has not been touched by the solar wind. It belongs to the galaxy, not to the sun. And almost nothing was known about it from direct measurement because no instrument had ever been there. Before Voyager 1, everything scientists thought they knew about the interstellar medium in our immediate galactic neighborhood was derived from remote sensing, from the absorption of starlight, from radio observations, from theoretical models built on top of other theoretical models, each inference resting on the one before it like a tall, carefully balanced stack. Some of those models were excellent. Some of them, it would turn out, were quite wrong. And the only way to know which was to send something there and look. This is worth pausing on. The very local interstellar medium is not the deep interstellar medium, not the space between spiral arms or the vast voids between galaxies. It is the space immediately next door to us, the galactic neighborhood immediately outside the sun's front door. And yet, before August 2012, no instrument built by human hands had ever touched it. We had been peering at it from the inside of the bubble, trying to infer its properties from the way it pressed against the boundary from the outside. Now, for the first time, something made by human civilization was actually in it. What the instruments found, piece by piece, over the months and years that followed, was a picture of the interstellar medium that was both more structured and more turbulent than many had expected. The first surprise was the magnetic field. Before Voyager 1 crossed the heliopause, many models had predicted that the magnetic field direction would change significantly at the crossing, that the direction of the sun's magnetic field on the inside of the boundary would be markedly different from the direction of the interstellar magnetic field on the outside. Voyager 1's magnetometer, operated by Leonard Balaga of NASA's Goddard Space Flight Center in Greenbelt, Maryland, found something unexpected. The direction of the magnetic field did change at the heliopause, but not by nearly as much as many models had predicted. The interstellar magnetic field and the heliospheric magnetic field were roughly aligned. This was either a coincidence or an indication that the local interstellar magnetic field has been shaped over time by the presence of the heliosphere itself, distorted and redirected by the bubble's existence over billions of years of close proximity. Neither explanation is fully satisfying, and as of today, the question of magnetic field alignment at the heliopause remains one of the more actively debated topics in heliospheric physics. The second surprise concerned the density of the interstellar plasma itself. The boundary, called the heliopause, was expected to be marked by a large increase in plasma density, from about 0.002 electrons per cubic centimeter in the outer heliosphere to about 0.1 electrons per cubic centimeter in the interstellar medium. What Gurnett and his colleagues actually measured was an electron density of about 0.08 per cubic centimeter, somewhat below the expected value, but within the range that models had suggested was plausible. More interesting than the number itself was what happened to it in the years following the crossing. It increased. Not dramatically, not all at once, but steadily, a gradual rise in electron density as Voyager 1 moved deeper into interstellar space. This was something that had not been widely anticipated. Most models had treated the density of the local interstellar medium as roughly uniform, a relatively constant background medium into which the heliosphere sat like a bubble in a tank of liquid. What Voyager 1's plasma wave data revealed instead was a large-scale density gradient, a region in which the plasma becomes progressively denser as you move away from the heliopause and deeper into interstellar space. The Voyager 1 plasma wave system gave point estimates of the plasma density spanning about 30 astronomical units of interstellar space, revealing this large-scale density gradient and evidence of turbulence outside the heliopause. Turbulence. That word deserves attention. When scientists describe the interstellar medium as turbulent, they mean something specific and physical. Fluctuations in density, velocity, and magnetic field that vary over a wide range of spatial scales, driven by processes that cascade energy from large scales to small ones, like the turbulence in a fast-moving river, but operating over distances measured in astronomical units and driven by energies that dwarf anything in a river. The very local interstellar medium, despite being referred to as a medium, which implies a kind of background uniformity, is actually a restless, dynamic, fluctuating environment. It is not a still lake. It is more like an ocean with weather. Now, consider what this means for understanding the local galactic environment. For decades, the standard picture was that the Sun sits in a region of the galaxy called the local bubble, a large, roughly cylindrical cavity in the interstellar medium, roughly 1,000 light-years across, that was apparently carved out by a series of supernova explosions sometime in the last few million years. Within this local bubble, the interstellar medium is thought to be significantly less dense and hotter than typical galactic values. The Sun happens to sit inside this cavity, which means the interstellar medium pressing against the heliosphere from the outside is relatively thin. And Voyager 1's measurements of plasma density in the very local interstellar medium are, in part, confirming and refining our picture of this local galactic environment. But confirming a general picture is different from mapping its details. And the details, as Voyager 1 is demonstrating, are complex. Pause here, because the geometry of what is happening is easy to lose track of in the accumulation of technical detail. Picture yourself standing in the center of an enormous spherical room. The walls of the room represent the heliopause, the edge of the Sun's domain. You are standing approximately where the Earth would be, though in this imagined scale, the Earth is invisible, a microscopic point in the center of the room. The entire planetary system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, would fit in a region smaller than a grain of sand, relative to the size of this room. The room's walls are roughly 120 astronomical units away, which in real space means about 18 billion kilometers. The wall is not smooth. It is irregular, dented and bulged by the pressure of the interstellar medium from outside and the variable pressure of the solar wind from within. Beyond the wall is where Voyager 1 now travels. It has been moving through that external region, the very local interstellar medium, for more than a decade. In human terms, it takes light about 23 hours to travel from Earth to where Voyager 1 is now. When you send a command to the spacecraft, it takes nearly that long for the signal to arrive. When Voyager 1 responds, it takes another 22 or so hours for the response to reach us. Every exchange with this machine is a 2-day conversation, and the signals that come back are vanishingly faint. The transmitter aboard Voyager 1 produces about 22 watts of power, roughly the power of a dim refrigerator light bulb. By the time that signal crosses 24 billion kilometers and arrives at Earth's largest dish antennas, its power has been reduced to a level so inconceivably small that it requires some of the most sensitive receiving equipment ever built to detect it at all. The fact that it is still arriving is itself an engineering achievement of the first order. This is the right moment to introduce the spacecraft itself more fully, because understanding what Voyager 1 is, physically, structurally, is essential for appreciating both what it has been able to detect and what it has not. Voyager 1 was launched on September 5, 1977, from Cape Canaveral, Florida. It is a relatively compact machine, roughly the size of a small car, weighing about 815 kilograms at launch, including fuel, with a dry mass of roughly 722 kilograms. Its scientific instruments were arranged on 2 booms extending from the main bus. One, a long magnetometer boom, designed to keep the sensitive field detectors away from the mild magnetic interference of the spacecraft itself, and another, shorter boom carrying several particle and plasma instruments. A large, dish-shaped high-gain antenna, 3.7 meters across, pointed toward Earth and served as both the spacecraft's receiver and its transmitter. At launch, Voyager 1 carried 11 scientific instruments. Some of those instruments have long since ceased to function. The plasma spectrometer, the instrument that would have directly measured the density and velocity of the plasma around the spacecraft, stopped working shortly after the Saturn encounter in 1980. This loss turned out to be enormously consequential, because it meant that for the entire journey through the outer heliosphere, the heliosheath, and into interstellar space, Voyager 1 had no direct plasma measurement capability. It had to infer plasma conditions from indirect measurements, primarily from the plasma wave subsystem, which could detect the frequency of electron oscillations and use that to calculate electron density, but only when the right conditions were met. Without the plasma spectrometer, confirming the heliopause crossing took more than a year longer than it would have otherwise. As of 2026, only 2 instruments are operational on Voyager 1, the plasma wave subsystem and the magnetometer. These are, in many ways, the right 2 instruments to have. The plasma wave subsystem continues to track the electron density of the interstellar medium as the spacecraft moves deeper through it, mapping the turbulence and the density gradient that it has been revealing for more than a decade. The magnetometer continues to track the direction and strength of the interstellar magnetic field, providing the only direct in situ measurements of the local galactic field available to science. Together, these two instruments are doing the most scientifically relevant work that Voyager 1 can do in the very local interstellar medium. And they will continue doing it until the power finally runs out, which could be sometime in the 2030s. Both Voyagers get energy from a generator that turns heat from decaying plutonium into electricity, and they lose about 4 watts of power every year. That is a slow, relentless drain on a system that started with roughly 470 watts at launch and has been declining ever since. Each watt that disappears represents a choice: which instruments to keep running, which to sacrifice in order to preserve the ones that matter most. These are not abstract engineering decisions. They are choices about which questions the mission will still be able to answer, and which questions will go permanently unanswered once the power is gone. On April 17th, 2026, NASA turned off Voyager 1's low-energy charged particles experiment, the instrument that had been measuring ions, electrons, and cosmic rays, data that had helped scientists understand the structure of the interstellar medium for nearly 5 decades. The choice preserved power for the instruments that remain. The people making these choices are not indifferent to the weight of them. Voyager mission manager Karim Badaruddin put it plainly: while shutting down a science instrument is not anybody's preference, it is the best option available. Every instrument lost is a window closed onto a part of the universe that no other mission can currently observe. There is no replacement coming, not soon. It is worth understanding why. The journey that Voyager 1 has taken, more than 24 billion kilometers in nearly 50 years, was only possible because of a rare gravitational opportunity that comes around once every 175 years or so. A planetary alignment that allowed the spacecraft to use the gravitational pull of the outer planets as a series of slingshots, each one adding velocity to the spacecraft and redirecting it toward the next. This gravity assist trajectory, developed in detail by mathematician Gary Flandreau at the Jet Propulsion Laboratory in Pasadena during the mid-1960s, was the reason NASA could reach the outer solar system at all in any reasonable timeframe. Without it, a spacecraft launched on chemical propulsion alone would have taken many decades more to reach even the termination shock. Flandreau recognized the opportunity in 1965, and a window opened in the late 1970s. Voyager launched in 1977, precisely when the alignment was available, and has been moving away from the Sun ever since, currently traveling at roughly 17 kilometers per second relative to the Sun. No spacecraft launched since has been aimed at the heliopause with similar speed or trajectory. A future interstellar probe, something the scientific community has been discussing and planning for years, could potentially be designed to move faster using nuclear propulsion or solar sails or advanced gravity assists to reach the termination shock in decades rather than half a century. But such a mission is years or decades from launch, and the political and financial will to fund it is uncertain. In the meantime, Voyager 1 is the only data point we have from beyond the heliopause. One spacecraft, one trajectory, one narrow sample from a region that stretches in all directions and varies enormously depending on which way you look. This is a fundamental limitation that should be named explicitly. A single spacecraft provides a single one-dimensional sample of a three-dimensional structure. Voyager 1 is moving roughly in the direction of the constellation Ophiuchus, broadly toward the galactic north. Voyager 2 is moving in a different direction, roughly southward toward the constellation Telescopium. Their crossing of the heliopause happened at different times and at slightly different distances. Voyager 1 at about 121.6 astronomical units in 2012, Voyager 2 at about 119.7 astronomical units in 2018. These two different crossing distances and directions already tell us something about the shape and asymmetry of the heliosphere. The heliopause is not a perfect sphere, and the two probes sampled it at different points on an irregular surface. Some researchers argue that the density differences measured by the two plasma wave instruments at their respective heliopause crossings are probably due to their relative locations in the boundary layer that forms in the interstellar plasma just beyond the heliopause. Others are not so certain, and the debate about the fine structure of the heliopause, whether it is smooth or layered, whether it is in steady state or constantly fluctuating, is ongoing. What both spacecraft agree on is this: the interstellar medium beyond the heliopause is not what the textbooks described. It is denser than expected in some places, more turbulent than expected everywhere, more magnetically complex than many models had assumed. And in 2021, a paper published in the journal Nature Astronomy by Stella Koch-Ocker, a doctoral student at Cornell University's Department of Astronomy, along with colleagues James Cordes and Shami Chatterjee, and University of Iowa scientists Donald Gurnett and William Kurth, added something genuinely new to this picture. Ocker and her colleagues had been analyzing the Voyager 1 plasma wave system data, not just for the episodic bursts of plasma oscillation that had been the main tool for measuring interstellar density, but for something subtler, a very weak, extremely narrowband signal that seemed to persist continuously in the data from 2017 onward. This faint, steady emission, unlike anything that had been previously identified in the Voyager data, appeared to be present, not just when a solar shockwave was conveniently triggering plasma oscillations, but all the time, regardless of what the sun was doing. That steady signal turned out to be something profound, a hum, a continuous whisper from the interstellar medium itself. The plasma wave system measures these signals as narrow features in frequency-time spectra, extremely thin lines in the data, barely wider than 0.2 to 0.4 kilohertz, hovering close to the local plasma frequency of the surrounding gas. What Ocker and her colleagues had detected was a class of very weak, narrowband plasma wave emission that persists from 2017 onwards and enables the first steadily sampled measurement of the interstellar plasma density over about 10 astronomical units, with an average sampling distance of 0.03 astronomical units. Instead of point estimates triggered by solar events, they now had something approaching a continuous profile, a running measurement of the plasma density as Voyager 1 drifted deeper and deeper into the galaxy's outer reaches. This persistent hum was not a radio broadcast. It was not a signal from anything alive. It was the quantum mechanical noise of electrons in the interstellar plasma settling into their lowest thermal energy states, an emission so faint that it takes the combined sensitivity of a plasma wave instrument built in the 1970s and decades of patient data analysis to even detect. But it was real, and it was continuous, and it was telling scientists something that nothing else could. What the density of the interstellar medium is like, not just at isolated moments when the sun conveniently provides a triggering event, but steadily, as a function of distance, as the map of the region gradually extends. The immediate finding from this analysis was the confirmation and refinement of the density gradient. The interstellar plasma gets progressively denser as Voyager 1 moves away from the heliopause. Density fluctuations at the scale of astronomical units were found tracing interstellar turbulence between episodes of previously detected plasma oscillations. This density gradient is not fully understood. Some researchers think it reflects a physical boundary further out, a shell or cloud of denser interstellar material in the galaxy's local structure. Others suggest it may be related to the specific trajectory Voyager 1 is taking, which happens to pass through a region of the very local interstellar medium that is not representative of the broader environment. We do not yet know which interpretation is correct. This is one of several points in the Voyager story, where what the data shows is clear, but what it means is genuinely contested. Something here deserves reflection, because the 2021 discovery of the persistent plasma hum changed the nature of what the Voyager 1 mission is. Before this discovery, the plasma wave science from the mission depended on the sun. Every time scientists wanted to know the electron density of the surrounding interstellar medium, they had to wait for the sun to obligingly launch a coronal mass ejection. Wait for the shock wave to propagate outward through the heliosphere over a period of months. Wait for it to hit the heliopause and push a disturbance through into the interstellar medium. Wait for that disturbance to arrive at Voyager 1 and trigger plasma oscillations, and then measure those oscillations to infer the local density. The whole process from solar event to scientific measurement could take 1 to 2 years. It was episodic, unpredictable, and dependent on a star 24 billion kilometers away, doing exactly the right thing at the right time. Now, with the persistent hum identified, the plasma wave subsystem is essentially a continuous density probe. It no longer needs the sun's cooperation. It is, in a sense, listening to the interstellar medium speak for itself, detecting the faint electromagnetic voice of the gas between the stars as that gas quietly, perpetually, at every point in space, radiates the thermal noise of its own existence. This is a conceptual shift of some importance. It means that the measurements Voyager 1 can make in the years remaining to it are not just confirmations of a known picture. They are an expanding map of a region that no previous measurement has ever directly characterized. Every astronomical unit that Voyager 1 travels from now until the day its power finally fails is a new data point on the density profile of the very local interstellar medium. And that profile, as it extends, carries information about the structure of the galactic environment surrounding our solar system, about how the local bubble is structured, about where the next density boundary might be, about what lies between us and the nearest stars. There is a mystery embedded in this picture that deserves its own careful attention, and we will arrive at it fully in due course. But to understand it, we need to first understand what the heliosphere looks like from the outside, not from the Voyager 1 perspective of a single narrow trajectory moving outward through the layers, but from a broader vantage point that encompasses the entire bubble and asks what shape it actually takes in 3 dimensions. The answer to that question came from an entirely different mission, using an entirely different method, and it produced a picture of the heliosphere that surprised nearly everyone who had been working on the problem. Stand for a moment at the far edge of the very local interstellar medium, at the point where Voyager 1 currently drifts. You cannot see the sun from here, not with the naked eye. It is a star among stars, a single bright point in a field of thousands, distinguishable only if you know precisely where to look. Around you, in every direction, is the flat darkness of interstellar space, not truly empty, but so close to empty that the distinction barely matters. A few atoms per cubic centimeter, magnetic field lines threading through the gas, ghostly and invisible, oriented roughly parallel to the galactic plane. The occasional high-energy cosmic ray, a particle accelerated to near light speed by some distant supernova or pulsar, hissing through the plasma like a bullet. It is a place of extraordinary, almost physical silence. Not the artificial silence of a recording studio, but the silence of a genuinely sparse medium, a place where the distances between particles are so vast that they interact with each other only rarely and slowly, where the timescales of physical processes are measured not in seconds, but in years and centuries and longer. And pressed up against this medium, visible in some sense if you could perceive magnetic fields and energetic particles, is the outer surface of the heliosphere, the heliopause, from the outside, seen as the place where the sun's material stops and the galaxy's material begins. What does that surface look like? For decades, the canonical picture was a roughly teardrop or comet-shaped bubble, round and blunt on the sunward side, where the solar wind pushes outward against the interstellar medium head-on and elongated into a long tail, called the heliotail, on the downwind side, where the heliosphere trails behind the sun like the tail of a comet. The analogy was clean, the physics was reasonable, and the picture was widely reproduced in textbooks and science journalism alike. The heliosphere, moving through the galaxy at roughly 26 kilometers per second, relative to the surrounding interstellar medium, should carve out a comet-shaped cavity, with the blunt end facing the direction of travel and the tail extending for enormous distances behind. Here is where the simple version begins to collapse once you look closer. In 2008, NASA launched a small, ingenious spacecraft called the Interstellar Boundary Explorer, known by its acronym IBEX, to a high orbit above Earth. Its first full-sky maps, published in 2009, revealed something nobody had predicted. Its goal was to map the heliosphere from the inside out, not by traveling to the boundary, but by detecting a specific type of particle called an energetic neutral atom, or ENA. These particles originate at the termination shock and in the heliosheath, where the hot solar wind plasma interacts with the cold neutral gas that flows in from the interstellar medium. When a fast-moving solar wind proton collides with a slow-moving interstellar neutral atom, they can exchange an electron. The proton becomes a neutral atom moving fast. The neutral becomes a slow ion. The fast neutral atom, now electrically neutral, is not deflected by magnetic fields. It flies in a straight line, outward in all directions. Some of those lines point back toward Earth. IBEX's detectors catch them. By building up a statistical map of energetic neutral atoms arriving from all directions of the sky, IBEX can essentially take a photograph of the heliosheath from the inside, a global image of the termination shock and the region beyond, seen in the currency of these neutral atom emissions. What the IBEX team, led by David McComas at Southwest Research Institute in San Antonio, Texas, found when they published their first full-sky map in 2009 was something nobody had predicted. There was a bright ribbon, a long curving stripe of enhanced energetic neutral atom emission arcing across the sky in a band that matched no feature in any existing model of the heliosphere. It was bright, coherent, and unmistakable. Every theoretical prediction for what IBEX would see had been wrong. The ribbon was real, reproducible, and completely unexplained. The IBEX ribbon, as it quickly came to be called, sparked an intense period of theoretical activity. One set of proposals argued that the ribbon was a region where reflected solar wind ions, interacting with the interstellar magnetic field, were being sent back toward the sun. Another set argued that it marked the location where the heliospheric magnetic field and the interstellar magnetic field are very nearly perpendicular, a condition that creates a specific physical instability in the plasma that could produce the observed emission. A third class of models invoked the structure of the heliosphere's outer boundary layer in more complex ways. Some researchers think one interpretation is correct. Others think another interpretation fits the data better. As of today, The origin of the ibex ribbon remains one of the open questions of heliospheric physics, and the answer, when it comes, will almost certainly tell us something important about the geometry of the interstellar magnetic field surrounding our solar system. More immediately relevant to the shape of the heliosphere, ibex also provided evidence that challenged the comet tail picture. The heliosheath energetic neutral atom data suggested that the tail, the heliotail, was not the elongated, smooth, comet-like structure that models had predicted. Instead, it appeared to be divided into at least two lobes, structured and irregular, rather than smooth and symmetric. Combined with additional data from the Cassini spacecraft, which was orbiting Saturn but also happened to carry a detector capable of detecting ENAs, and with later observations from the IBEX mission itself, a new picture began to emerge of a heliosphere that is considerably more complex in shape than the textbook comet model. Some models now suggest the heliosphere may be shaped more like a croissant than a comet. With two lobes extending behind the Sun in the tail direction, produced by the winding structure of the heliospheric magnetic field as the solar wind spirals outward. Others suggest that the tail is shorter than previously thought, perhaps because the interstellar magnetic field is strong enough to prevent the formation of the long, comet-like extension. Still others argue that the shape changes significantly with the solar cycle, pulsing and varying in ways that a simple, steady-state model cannot capture. We cannot know the true three-dimensional shape of the heliosphere from within it, at a single point in time, with measurements from just two spacecraft moving in two specific directions. This is one of the genuinely irreducible limitations of the observational situation we are in. It is not a limitation that more clever analysis will overcome. It is a fundamental constraint on what is knowable from the inside. A future mission that placed a probe or an array of probes at multiple points around the heliosphere's outer boundary, sampling different cross-sections simultaneously, would be transformative. No such mission currently exists. We are now roughly 130 astronomical units from the Sun, drifting through the very local interstellar medium with Voyager 1, and the picture of the heliosphere from the outside has turned out to be considerably stranger than the models predicted. The shape is uncertain. The tail is irregular. The ribbon of energetic neutral atoms that IBEX revealed has no fully satisfying explanation. And the plasma through which Voyager 1 moves is not the smooth, uniform background that many had assumed, but a turbulent, gradually thickening medium with density fluctuations on scales from fractions of an astronomical unit to many astronomical units. But there is something else happening out here that we have not yet addressed, something that connects what Voyager 1 is finding in the interstellar medium to a much larger question about the relationship between our solar system and the galaxy around it. Something that, when you understand it fully, changes how you think about the Sun, about the heliosphere, and about what it means to live inside a stellar bubble in a galaxy full of other stellar bubbles. To reach it, we need to go back to the termination shock crossing and follow a different thread through the data, not the thread of plasma density, but the thread of energetic particles. Cosmic rays. The textbook answer about cosmic rays is that they come from distant sources, supernovae, pulsars, active galaxies, and fill the galaxy uniformly, like a kind of high-energy background radiation. They are charged particles, protons, helium nuclei, electrons, moving at velocities that approach the speed of light, carrying energies that dwarf anything produced by the Sun. The textbook version says these particles are present everywhere, that they stream through the galaxy with only minor variations in density from one place to another, and that the heliosphere provides some degree of shielding from them. The closer you are to the center of the heliosphere, the more the solar wind's magnetic field has deflected and slowed the incoming cosmic rays, reducing their intensity. By the time cosmic rays reach the inner solar system, their numbers have been significantly reduced from what they would be in open interstellar space. This process, the reduction of cosmic ray intensity by the sun's magnetic wind, is called solar modulation. And one of the clearest predictions of solar modulation theory is that when Voyager 1 crossed the heliopause and exited the heliosphere, the intensity of galactic cosmic rays should jump. Outside the bubble, there is no solar wind to provide shielding. The cosmic rays should be at their full, unmodulated intensity, higher than anything measured inside the heliosphere, particularly at lower energies where the solar wind's influence is strongest. That prediction turned out to be exactly right. In the months leading up to and following the August 2012 heliopause crossing, Voyager 1's cosmic ray instruments recorded a dramatic change. The intensity of cosmic rays coming from outside the heliosphere, galactic cosmic rays, increased sharply and then stabilized at a level distinctly higher than anything seen inside the bubble. At the same time, the intensity of solar energetic particles accelerated by the sun and by processes within the heliosphere, dropped sharply and essentially disappeared. It was as if a valve had opened on one side and closed on the other, out of the bubble into the galaxy. Edward Stone, in 2013, described these observations as providing clear evidence of the crossing. The intensities of particles had reached a steady plateau that was consistent with the fully unmodulated galactic cosmic ray spectrum, a spectrum that models had been predicting, but that no instrument had ever directly confirmed from the inside of the galaxy. But here is where things become genuinely complicated. Before Voyager 1 crossed the heliopause, during its long traverse of the heliosheath, the cosmic ray data had been telling a more ambiguous story. There had been periods, months-long intervals, during which the intensity of galactic cosmic rays seemed to jump toward their interstellar values, as if Voyager 1 had momentarily gotten a glimpse of the outside before falling back to the modulated levels expected inside the heliosphere. Krimagis and colleagues had been puzzling over these transients for years. Some researchers suggested that Voyager 1 had been temporarily crossing the heliopause back and forth, that the boundary was moving, oscillating in response to changes in the solar wind pressure, and that Voyager was sampling both sides. Others suggested that the transients were caused by magnetic connection events, brief moments when magnetic field lines inside the heliosphere connected to field lines outside, creating conduits through which cosmic rays could temporarily flow inward. Still others thought the structure of the heliosheath itself was more complex than a simple layered model, with channels and corridors of different plasma properties that could produce cosmic ray variations without requiring any actual crossing of the heliopause. The debate over the interpretation of these transient events illustrates something important about the difficulty of doing science at the edge of the solar system with a single spacecraft. When you have one data point, the range of explanations that are consistent with it is always large. The data is real. The phenomenon is real. But the mechanism behind it could be any of several quite different physical processes, and distinguishing between them requires either more data, more locations, more instruments, more time, or a theoretical framework powerful enough to rule out alternatives. The heliospheric community had and has spirited disagreements about these questions, and those disagreements are not a sign of confusion. They are a sign that the science is genuinely hard and the phenomena genuinely complex. What is not disputed is the final picture. Outside the heliopause, the cosmic ray environment is qualitatively different from the one inside. The galaxy, the full, unshielded galactic cosmic ray environment, is the medium through which Voyager 1 now moves. And that environment is not as benign as the shielded inner solar system. This is worth sitting with for a moment. Every living thing on Earth, every bacterium, every tree, every human being, exists beneath multiple layers of protection from the galactic cosmic ray flux. The Earth's atmosphere absorbs most of the incoming high-energy particles before they can reach the surface. The Earth's magnetosphere deflects a significant fraction before they even enter the atmosphere. And underneath all of that, the heliosphere itself provides a first layer of shielding, a bubble of magnetic field and plasma that reduces the incoming cosmic ray intensity, particularly at lower energies, by a meaningful fraction. Remove the heliosphere, and the surface dose of cosmic radiation on Earth would increase. Not catastrophically, the atmosphere and magnetosphere would still be there, but measurably. The heliosphere is, among its many other roles, a shield. For human beings thinking about traveling to other star systems, or even spending extended periods far from the Sun in the outer heliosphere or beyond, this is not an abstract concern. The galactic cosmic ray flux in interstellar space is the primary long-term radiation hazard for deep space missions. More persistent, harder to shield against, and more damaging over multi-year timescales than the solar energetic particle events that dominate the radiation environment in the inner solar system. Understanding its true spectrum and intensity from direct measurement at Voyager 1's location is one of the mission's most practically important ongoing contributions. We have been moving steadily outward through the layers of the solar system's edge, and we are now fully outside the heliosphere in the interstellar medium. But the story does not end there, because even in the interstellar medium, even beyond the Sun's direct domain, the Sun's influence is not entirely absent. The Sun speaks into interstellar space. Not continuously, not in the same way as the solar wind, which is stopped at the heliopause, but periodically in the form of pressure pulses, great waves of compressed plasma and magnetic field produced by powerful eruptions on the Sun's surface called coronal mass ejections. These eruptions launch enormous clouds of magnetized plasma outward through the solar wind at speeds far exceeding the background wind. They travel through the heliosphere, across the termination shock, through the heliosheath, and when they reach the heliopause, they push against it from the inside, sending a pressure wave, a shock, through into the interstellar medium. Those interstellar shocks can propagate outward for enormous distances from the heliopause. They travel more slowly in the denser, colder interstellar medium than they did in the solar wind, but they keep moving, gradually weakening as they go. When one of those shocks reaches Voyager 1, the plasma wave instrument detects it as a sudden change in the local electron oscillation frequency. The density around the spacecraft momentarily spikes as the compressed plasma of the shock front sweeps through. Scientists, including Adam Szabo at NASA's Goddard Space Flight Center, have described this as pressure pulses moving past the spacecraft from events on our Sun. In this way, Voyager 1 is able to detect how the Sun interacts with the interstellar environment, a kind of seismology of the heliosphere, where shocks generated by solar events propagate outward like seismic waves and are recorded by a distant instrument. The very property that makes these shocks useful for measuring plasma density, their ability to trigger plasma oscillations, is what made them the primary tool for density measurements before the persistent hum was discovered. The sequence of shock detections between 2012 and 2021 produced a series of snapshot density measurements at different distances from the heliopause. and those snapshots were what first revealed the density gradient in the very local interstellar medium. Each shock was, in a sense, the sun reaching out a long arm and ringing a bell far beyond its own boundary, and listening to the note to determine what kind of space lay around the spacecraft. The fact that solar shocks can propagate into the interstellar medium is one of the lines of evidence that the heliosphere is not a perfectly sealed container. There is interaction across the boundary, not just the large-scale interaction that shapes the heliopause, the pressure balance between solar wind and interstellar medium, but small-scale transient interactions, shocks passing through, magnetic field lines occasionally connecting across the boundary, neutral atoms from the interstellar medium flowing through the heliopause into the heliosphere in both directions. The heliosphere is porous in ways that the simple model, heliosphere here, interstellar medium there, clean boundary between them, does not capture. And in 2020, something changed in the measurements from Voyager 1's magnetometer that pushed this porosity to the front of scientific attention. In 2020, Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic fields embedded in the tenuous interstellar plasma, while its plasma detector measured a rise in plasma density. Similar anomalies had been seen before, spikes in plasma density and magnetic field strength associated with solar shock arrivals. But those earlier events had faded back to baseline after a few months, following the expected pattern of a transient shock sweeping past. This new anomaly, which began in 2020, did not fade. The density stayed elevated. The magnetic field stayed elevated. And as months passed, and then a year passed, and then 2 years passed, the anomaly persisted, not decaying, not returning to baseline, simply staying high. Researchers believe the transient jumps seen before were generated when surges of plasma streaming outward from the sun smashed against the boundary of the heliosphere, creating swells that reverberated through interstellar space, compressing interstellar plasmas and intensifying their magnetic fields. That explanation worked for the earlier transient events. But the anomalies that began in 2020 did not abate, leading some mission scientists to question whether they originated with the sun at all. This is a genuine scientific mystery. The data is unambiguous. Something changed in the environment around Voyager 1 in 2020 and has not changed back. The interpretation is not. One possibility is that Voyager 1 has drifted into a distinct region of the very local interstellar medium, a cloud, a filament, a region of denser gas that simply happens to have higher density and stronger magnetic fields than the region it was in before. The interstellar medium is not uniform, and the very local interstellar medium through which our solar system moves has structure on all scales, including the scale of tens of astronomical units. If Voyager 1 has entered a denser cloud, the elevated readings would simply reflect the properties of that cloud, rather than any particular dynamical event. Another possibility is that the 2020 anomaly is a long-duration pressure event, a particularly powerful or sustained series of solar eruptions whose compressive effects on the heliopause and beyond have persisted for years rather than months. The sun's activity cycle was approaching solar maximum around this period, which means activity was increasing, and the solar wind pressure was generally higher. A third possibility, more speculative but not easily dismissed, is that Voyager 1 has crossed an internal boundary within the very local interstellar medium, an interface between two distinct plasma regions that has no analog in the heliospheric models, built on the assumption that the medium outside is roughly uniform. In this interpretation, the 2020 transition marks the entry into a genuinely different kind of interstellar space, one whose properties will not return to the earlier baseline, because there is a structural reason for the difference, not a transient one. Before the communications crisis of November 2023, when Voyager 1 began sending garbled data back to Earth, the mission had been actively investigating this mystery. The communications blackout lasted approximately 6 months. After painstaking remote diagnostics, the team identified the culprit: a single failed memory chip inside the flight data subsystem, one of 3 onboard computers. The chip held about 3% of that subsystem's memory, including code essential for packaging science and engineering data before transmission. Whether a cosmic ray killed it or the silicon simply gave up after 46 years in the void, nobody can say for certain. The entire usable memory of that computer is 69.63 kilobytes, roughly the size of a low-resolution thumbnail image. The fix required engineers to break the corrupted code into fragments, find empty corners of the memory where the pieces would fit, rewrite the chunks so they would still function as a whole, and beam the patch to a spacecraft so distant that each command took 22.5 hours to arrive. On April 20th, 2024, Voyager 1 started transmitting coherent data again. It was, in the words of Todd Barber, the mission's propulsion lead at JPL, another miracle save for Voyager. The resilience of the mission, its improbable decade-upon-decade continuation through crises that would have ended any less carefully built machine, is itself a kind of story running parallel to the scientific narrative. But the scientific narrative is what matters most here, and the 2020 anomaly, the unexplained rise in density and magnetic field strength that has persisted for years, is the most pressing open question the mission now faces. It is the thing that scientists were eager to investigate when the communications were restored in 2024. And it is the thing that the remaining instruments, the plasma wave subsystem and the magnetometer, are best positioned to characterize. Take a moment to look back at the path we have traced. We began at the sun. We moved outward through the solar wind, that constant exhalation of charged particles flowing in all directions at hundreds of kilometers per second. We crossed the termination shock at roughly 94 astronomical units in 2004, the standing wave where the supersonic wind slows abruptly, heating and compressing. We moved through the heliosheath, the thick, turbulent zone of slowed solar wind, for 8 years. We crossed the heliopause in August 2012, confirmed a year later by the plasma oscillation measurements made by Donald Gurnett's instrument at the University of Iowa, and entered the very local interstellar medium. We found a denser, more turbulent medium than models had predicted, with a persistent density gradient extending outward. We found a continuous plasma hum, first identified in 2021 by Stella Koch-Ocker and her Cornell colleagues, that allows continuous measurement of the local electron density. And we found, beginning in 2020, an anomaly, a sustained elevation of density and magnetic field, whose cause remains genuinely unknown. Each of these layers has been stranger than the layer before it. Each one has taken something that looked simple from a distance and revealed hidden complexity up close. The solar wind looked uniform. It was not. The termination shock looked like a place where cosmic rays would peak. They peaked somewhere else. The heliopause looked like a clean boundary. It is porous and fluctuating. The interstellar medium looked like a calm background. It is turbulent and structured. And the structure of the heliosphere from the outside, which should have been a simple comet shape, is irregular, asymmetric, and contains a ribbon of emission that no model anticipated. This is the pattern. This is what Voyager 1 has been teaching us, layer by layer, boundary by boundary. that the universe does not simplify when you look more closely at it. It deepens. And we have not yet reached the deepest layer of this story. That layer concerns something that connects the Voyager findings to a much larger question. A question about time as well as space. About the history of the solar system's journey through the galaxy. About what has happened to the heliosphere in the past and what might happen to it in the future. A question that, when you sit with it long enough, begins to feel less like a technical problem in heliospheric physics and more like an existential one. But to reach that question, we need to understand one more physical structure, one more layer of hidden complexity that Voyager 1's data has begun to illuminate. A structure called the bow shock, or rather, the possible absence of one. The bow shock, in the traditional model of the heliosphere, was supposed to be the outermost boundary of the heliosphere's interaction with the interstellar medium, a supersonic shockwave forming ahead of the heliosphere as the sun's bubble plows through the galaxy at roughly 26 kilometers per second. By analogy with a supersonic aircraft generating a shockwave ahead of it in the atmosphere, the heliosphere was expected to generate a standing shockwave in the interstellar medium ahead of its motion, a place where the interstellar gas, unable to get out of the way of the approaching heliosphere fast enough, piles up and suddenly slows, heating as it does so. For decades, the bow shock was treated as essentially given. Models included it. Textbooks mentioned it. It was a standard feature of the heliospheric picture. Then, in 2012, a team using IBEX data, led by David McComas, revisited the question with new measurements of the speed at which the heliosphere is moving, relative to the surrounding interstellar medium, and found something surprising. The speed was lower than previous estimates had assumed, roughly 23 kilometers per second, rather than the 26 or so that older measurements had suggested. The difference is not enormous, but it matters enormously for the physics of the bow shock. Whether or not a bow shock forms depends on whether the heliosphere is moving faster than the magnetosonic speed, the speed at which disturbances propagate through the magnetized interstellar medium. Given the revised velocity and updated estimates of the interstellar magnetic field strength and plasma density, the conclusion was that the heliosphere might be moving below the threshold for bow shock formation. It might not have a bow shock at all. Some researchers have argued that the bow shock is real, just weaker than the traditional models assumed, or located at a much greater distance than previously thought. Others have accepted the IBEX analysis and concluded that the heliosphere is, in aerodynamic terms, subsonic relative to the interstellar medium, moving too slowly to pile up a true shockwave ahead of it. The evidence is not yet definitive. What is clear is that the confident textbook picture of the bow shock, one of the standard features of heliospheric geometry, is now contested, and whether or not it exists is a question that will require either new measurements from beyond the heliopause or more sophisticated modeling to resolve. The possible absence of a bow shock is, in a sense, a perfect encapsulation of what the Voyager mission has meant for heliospheric science. The features that looked most certain from the inside, the ones most confidently drawn into models, have been the ones most thoroughly complicated by actual data. The termination shock turned out to be in the right place, but behaving in unexpected ways. The heliopause turned out to be a complex, porous, time-variable boundary rather than a clean wall. The interstellar medium beyond turned out to be turbulent and structured rather than smooth and uniform. And the bow shock, the outermost boundary, the one that was supposed to form ahead of the heliosphere as it moved through the galaxy, may not even exist. This is not failure. This is progress. This is what it looks like when a theoretical framework built on remote observations encounters direct measurement for the first time, and the discrepancies between prediction and reality reveal the places where the theory needs to grow. Now we turn to what lies further out still, not in distance along Voyager 1's trajectory, but in the larger context of what the heliosphere is embedded in. Because the very local interstellar medium that Voyager 1 is sampling is not the galaxy at large. It is a specific, historically contingent, locally unusual region. And understanding it requires zooming out to a scale that makes the entire heliosphere seem very small indeed. The Sun currently sits inside a region known as the local interstellar cloud, or sometimes the local fluff, a warm, relatively low-density cloud of gas, roughly 30 light-years across, through which the solar system has been moving for somewhere between 40,000 and 150,000 years. The local interstellar cloud is itself embedded within the larger local bubble, a roughly spherical void in the galactic interstellar medium, several hundred light-years across, bounded by a shell of denser gas and dust, apparently blown out by a series of supernova explosions that occurred in the last 10 to 20 million years. The hot, thin gas inside the local bubble is the medium in which our solar system is currently immersed. The properties of the local interstellar cloud are what determine the conditions that the heliosphere is currently experiencing. The density and temperature and magnetic field of the interstellar medium pressing against the heliopause from the outside. And those conditions are not eternal or fixed. The solar system is moving through this cloud at roughly 26 kilometers per second, and at that speed, the solar system will exit the local interstellar cloud within a few thousand to tens of thousands of years. When it does, the properties of the external medium pressing against the heliosphere will change. Some models suggest that when the solar system exits the local interstellar cloud, it may enter a denser region of the interstellar medium, possibly one of the other warm clouds in the local bubble. If it does, the increased external pressure will compress the heliosphere inward. The heliopause, currently at roughly 120 astronomical units from the Sun, would move closer. The heliosheath would thin. And, in extreme cases, if the external density were high enough, some models suggest that the heliosphere could be compressed so severely that the termination shock would move inside the orbit of Uranus, or even closer to the Sun. At that point, the protective shield that the heliosphere provides against galactic cosmic rays would be drastically reduced, and the cosmic ray flux in the inner solar system, the environment in which Earth and all its life exist, would increase substantially. This is not happening now, and the timescales involved are vastly longer than anything relevant to human civilization. But the possibility is real, and it has motivated a small but serious body of research into the history of the heliosphere's interaction with different interstellar environments over geological time, and into whether past excursions into denser interstellar clouds might have left any detectable signature in Earth's geological record. The question of what the heliosphere looks like when it is compressed, and what consequences that compression might carry for the inner solar system, is one of the most quietly profound questions to emerge from the Voyager mission's findings. It connects the physics of a boundary 120 astronomical units away to the biological history of a small planet at the center of the bubble. And to understand it fully, we need to spend some time with the evidence from Earth's own past. There is a thin layer of iron-60 in the deep ocean sediments of Earth, a radioactive isotope that does not form through ordinary geological processes and does not occur naturally in terrestrial rocks. Iron-60 is produced in supernova explosions and in the interiors of massive stars, and it has a half-life of about 2.6 million years. which means that any iron-60 present when the Earth formed has long since decayed into stable cobalt-60. If you find iron-60 in the sedimentary record, it came from space, and it came recently, within the last few tens of millions of years, because anything older would have decayed below detectability. In 2004, a team led by Günther Korschinek at the Technical University of Munich found a concentrated layer of iron-60 in a sediment core from the deep Pacific Ocean, dating to somewhere in the range of 2 to 3 million years ago. Further analysis revealed additional layers, and subsequent studies identified similar deposits in cosmic dust and on the lunar surface. The most widely accepted interpretation is that these iron-60 deposits were delivered to Earth from nearby supernova explosions. Explosions that occurred within perhaps a few hundred light-years of the solar system, and that launched a wave of heavy elements, including radioactive isotopes, outward through the local interstellar medium. Those elements eventually reached the heliosphere, passed through it, and settled on Earth. The supernova hypothesis is relevant here because it is those same supernovae, a series of them, occurring over the last 10 to 20 million years in what is called the Scorpius-Centaurus OB Association, a nearby region of recent star formation that are believed to have carved out the local bubble in which the solar system now sits. The supernovae blew away the surrounding interstellar gas, inflated an enormous hot cavity, and left the solar system embedded in a relatively thin, warm medium, the very medium that presses against the heliosphere today. The heliosphere is, in a sense, a product of those ancient explosions. The conditions that shape the outer boundary of our solar system today were set by stellar deaths that occurred millions of years before the first human beings appeared on Earth. This connection between supernova explosions millions of years ago and the structure of the heliosphere today is not a coincidence. It is a causal sequence, a thread of physical consequence stretching across millions of years of galactic history and arriving at the end at the boundary that Voyager 1 crossed in 2012. The heliosphere is not a permanent feature of the solar system in its current form. It is a historically contingent structure shaped by a specific local galactic environment that came into being at a specific time and will eventually change. Some researchers have proposed that there is a connection between the compression of the heliosphere during past encounters with denser interstellar clouds and events in Earth's geological and biological record. The logic runs as follows. If a dense interstellar cloud compressed the heliosphere severely enough to reduce its cosmic ray shielding, the resulting increase in cosmic ray flux at Earth's surface could, in principle, affect the rate of genetic mutation in organisms, alter atmospheric chemistry, or even play some role in longer-term climatic patterns. The evidence for this connection is suggestive but not definitive. Several researchers have noted temporal correlations between periods of increased galactic cosmic ray flux, inferred from cosmogenic isotopes in the geological record, and periods of significant evolutionary or climatic change. Others find the proposed mechanisms too weak or too indirect to be persuasive. This is one of those scientific questions where some researchers think the connection is real and important, while others remain unconvinced, and the honest answer is that the evidence is not yet strong enough to settle the matter. What is clear is that the heliosphere has not always been as it is today. It has been smaller and it has been larger, depending on the external pressure of the interstellar medium through which the solar system was passing. It has been shaped differently by different interstellar magnetic field orientations, and at some point in the relatively near future, on geological timescales, though not on human ones, it will change again as the solar system continues its orbit through the galaxy and eventually exits the local interstellar cloud. Voyager 1's measurements of the very local interstellar medium are, among other things, a snapshot of that cloud. They are the first direct samples of the medium that is currently compressing the heliosphere and setting its outer dimensions. The electron density that Donald Gurnett's instrument measured in 2013 and that Stella Koch-Ocker's 2021 analysis extended into a continuous profile is the density of the gas that is holding the heliopause at its current location. Change that density, compress the cloud, or exit it, and enter a denser one. And everything downstream changes with it. This is the deeper context into which the Voyager findings fit. They are not just measurements of a remote boundary. They are characterizations of a historically specific, physically contingent set of conditions that has existed for a finite time and will eventually be replaced by something different. We happen to be living in an era when the heliosphere is relatively large and protective, sitting in a relatively thin medium inside a large hot bubble blown by supernovae. That is not the default state of affairs for a star in this galaxy. It is a particular local condition, in a particular galactic neighborhood, at a particular moment in the solar system's 4.6 billion year history. Now we arrive at something that demands its own extended treatment, a feature of the Voyager story that initially seems like a footnote, but turns out to be one of the most scientifically important aspects of the entire mission. It concerns what Voyager 1 found at the termination shock, not the fact of the crossing, which was expected, but the way the energetic particles behaved near it. And it connects to one of the most fundamental questions in high-energy astrophysics. Where do cosmic rays come from? The standard model says that the termination shock is one of the sites where a particular class of energetic particle, called anomalous cosmic rays, is accelerated. Anomalous cosmic rays are particles that originated as neutral atoms in the interstellar medium, flowed into the heliosphere because they were electrically neutral and not deflected by the heliospheric magnetic field, were ionized by solar ultraviolet radiation or charge exchange near the sun, picked up by the solar wind, and then swept outward to the termination shock, where the shock acceleration process boosted their energies to anomalous, that is, unexpectedly high levels. The name anomalous refers to the fact that their energy spectrum is different from the expected galactic cosmic ray spectrum, as if they had been given a boost by some local source. The termination shock was the presumed acceleration site. It was a beautiful and internally consistent theory. It explained the origin of anomalous cosmic rays, the location of the acceleration, and the general shape of the energy spectrum. And then Voyager 1 reached the termination shock in December 2004, and the anomalous cosmic ray intensity did not peak there. Edward Stone's 2005 analysis was explicit. In contradiction to many predictions, the intensity of anomalous cosmic ray helium did not peak at the shock. The particles kept increasing in the heliosheath beyond the termination shock. They did not reach their maximum until Voyager 1 was well inside the heliosheath, moving toward the heliopause. This meant that either the termination shock was not the primary acceleration site, or that something else was happening in the heliosheath that was continuing to accelerate the particles after the shock crossing. Various explanations were proposed. Some researchers suggested that the termination shock acceleration was correct in principle, but that Voyager 1 happened to cross the shock at a location where the acceleration was less efficient, perhaps a dimple or weaker section of the shock surface, and that the particles were diffusing inward from a more distant, more efficient part of the termination shock somewhere else on its surface. Others proposed that the heliosheath itself was the true acceleration region, that the complex magnetic geometry of the compressed, turbulent heliosheath provided additional opportunities for stochastic acceleration, the process by which particles gain energy by bouncing between moving magnetic structures, gaining a little energy on each bounce, in a process sometimes compared to a ball gaining energy by bouncing between two approaching walls. A third class of models proposed something more radical, that anomalous cosmic rays are not accelerated primarily at the termination shock at all, but rather at the heliopause, the outermost boundary of the heliosphere, where the solar wind and interstellar medium meet and interact. This model, which has been developed and refined by several groups, predicts that the complex magnetic reconnection that occurs at the heliopause, where field lines from two different magnetic domains encounter each other and break and reconnect, provides an efficient mechanism for particle acceleration. The predictions of this model are different from those of the termination shock model in specific, testable ways. But testing them requires measurements very close to the heliopause, and Voyager 1's instruments were not ideally equipped for those measurements by the time it got there. This uncertainty about the acceleration site of anomalous cosmic rays is not a minor technical matter. Cosmic ray acceleration is one of the central problems of high-energy astrophysics, and the termination shock was supposed to be a nearby, accessible example of a process, diffusive shock acceleration, that is invoked to explain cosmic ray production in supernova remnants, pulsar wind nebulae, and other powerful astrophysical environments throughout the galaxy. If the termination shock does not cleanly demonstrate the process, it either means the process is more complex than assumed, or that the termination shock is not actually an efficient version of it, or that the analogy between the termination shock and more powerful astrophysical shocks is less clean than theorists had hoped. Some researchers lean toward one conclusion, others lean toward another. The Voyager data does not resolve the question. It sharpens it, focuses it, and makes some possibilities more plausible than others, but does not deliver a definitive answer. This is, again, the honest state of science. Picture yourself in the heliosheath, that thick, turbulent region between the termination shock and the heliopause, through which Voyager 1 traveled for 8 years. The solar wind that enters the termination shock at hundreds of kilometers per second and emerges on the far side moving at perhaps a tenth of that speed is not just slow. It is hot, heated by the shock compression to temperatures that are far higher than anything in the smooth, steady solar wind of the inner heliosphere. And it is turbulent. The magnetic field in the heliosheath is not organized into the neat spiral structure of the inner heliosphere, the Parker spiral, named after solar wind theorist Eugene Parker, who described it in 1958. In the heliosheath, the field is tangled, compressed, redirected by the pressure of the interstellar medium from outside and the continued outflow from the sun from inside. Magnetic bubbles, closed loop-like structures of magnetic field, have been detected in the heliosheath by both Voyager spacecraft, and they were not expected. Models had not predicted that the heliosheath would contain these kinds of large-scale magnetic structures, and their presence suggests that the geometry of the heliosheath is considerably more complex and perhaps more interesting for particle physics than a simple compressed wind region. Robert Decker, a physicist at the Johns Hopkins University Applied Physics Laboratory, and his colleague Stamatios Krimigis published detailed analyses of the particle environment in the heliosheath based on Voyager 1 data from 2005 onward, showing that the energetic particle behavior in the heliosheath was more complex and variable than the standard models had assumed. The flows of energetic particles were not smooth and steady. They fluctuated, reversed, showed evidence of large-scale structures within the heliosheath that were passing by Voyager 1 like weather systems. The heliosheath, far from being a featureless zone of compressed wind, was a dynamically active, structured environment with its own internal geography. And the magnetic bubbles deserve a moment of additional consideration because they carry a specific implication for what happens at the heliopause. If the heliosheath contains large-scale magnetic structures, enclosed, disconnected loops of magnetic field, then when those structures encounter the heliopause, they can interact with the interstellar magnetic field on the other side in ways that pure diffuse plasma would not. Magnetic reconnection, the process by which oppositely directed field lines break and reconnect in a lower energy configuration, releasing energy and accelerating particles, becomes possible or even likely at these structures, and magnetic reconnection at the heliopause is one of the candidate mechanisms for the particle acceleration that the anomalous cosmic ray data seems to be pointing toward. This is a fine example of how different threads of Voyager data weave together into a single, complex picture. The unexplained behavior of anomalous cosmic rays at the termination shock pointed toward the heliosheath and heliopause as possible acceleration sites. The detection of magnetic bubbles in the heliosheath provided a mechanism, magnetic reconnection, that could plausibly operate at the heliopause. And the properties of the heliopause, as characterized by Bulaga's magnetometer data and the plasma wave observations, provided the boundary conditions within which that reconnection could occur. Each piece of data constrains and illuminates the others. The picture is not complete. Important questions remain. The exact location of anomalous cosmic ray acceleration, whether it is predominantly at the termination shock, the heliosheath, the heliopause, or some combination of all three, is still debated. The role of magnetic reconnection in driving particle acceleration at the heliopause remains to be definitively quantified. The question of whether the termination shock's behavior is representative of diffusive shock acceleration in more powerful astrophysical environments, or whether it is a special and atypical case, is unresolved. But the overall picture that has emerged from Voyager 1's measurements of a termination shock that is real but behaviorally surprising, a heliosheath that is turbulent and magnetically structured, a heliopause that is porous and site of significant physical processes, and an interstellar medium beyond that is denser and more turbulent than expected, is coherent. It holds together. It points in specific directions for future investigation. And it is profoundly different from the picture that existed before Voyager 1 crossed the termination shock in 2004. We are now moving past the purely technical and into something that sits at the boundary between physics and philosophy, the place where the measurements end and the implications begin. Because embedded in everything Voyager 1 has found is a question that the data cannot answer directly, but that the data makes impossible to ignore. What does it mean that we can characterize the outer boundary of our solar system at all? Consider the epistemic situation. A machine built by human beings, using technology that was considered advanced in 1977 by the standards of 1977, has traveled for nearly 5 decades to a boundary 24 billion kilometers away, and has been sending back measurements of its environment that allow us to map with increasing precision the edge of our sun's domain. The instruments it carries are, by current standards, extraordinarily primitive. The plasma spectrometer failed 46 years ago. The computer memory is smaller than a low-resolution thumbnail. The transmitter puts out less power than a refrigerator light. And yet, the data it sends back has forced the rewriting of significant portions of heliospheric physics, has revealed that almost every feature of the heliosphere's outer boundary is more complex than the models predicted, has directly sampled a region of the galaxy that no other instrument has ever touched and continues to expand the map of the interstellar medium with every passing month. This is extraordinary on its own terms. But there is something more. Every single measurement that Voyager 1 has made, every density reading, every magnetic field direction, every cosmic ray count, every plasma wave frequency, has been made by instruments that were designed before the mission launched, that have been operating in interstellar space for more than a decade, and that are returning data so faint that it takes the largest antennas on Earth, pointed with exquisite precision, to detect it. The signal from Voyager 1 reaches Earth at a power level of about 10 femtowatts, 10 times 10 to the negative 15 watts. A femtowatt is a millionth of a billionth of a watt. The signal from the most distant human-made object ever built is arriving at the largest antennas in the deep space network, the 70-meter dishes at Goldstone in California's Mojave Desert, at Canberra in Australia, and at Madrid in Spain, at a power so small that it defies ordinary intuition. And those antennas, particularly the Deep Space Station 43 at Canberra, a 70-meter dish that is the primary receiving antenna for Voyager 1's trajectory, have their own story of fragility and maintenance. From May 2025 through February 2026, the Canberra antenna went offline for upgrades, with only brief periods of operation in August and December. During those months, commands to Voyager 1 were severely limited, and the window for urgent intervention, if something had gone wrong, was almost non-existent. The mission team had raced to fix Voyager 1's backup thrusters before the antenna went offline, knowing that if the primary thrusters failed during the communication blackout, there would be no way to respond in time. Engineers revived a set of primary roll thrusters aboard Voyager 1 that had been considered inoperable since 2004. The fix, completed in March 2025, just weeks before the Canberra antenna went offline, required creativity and risk, and the team succeeded just in time. The propulsion lead at JPL called it another miracle save. The vulnerability of the mission is not a bug. It is a fundamental feature of trying to maintain contact with a machine at the edge of the solar system with 1970s technology and an aging infrastructure on the ground. The Deep Space Network was not built exclusively for Voyager. It serves dozens of missions across the solar system. But for Voyager, it is the only lifeline. When DSS-43 goes offline, Voyager 1 is effectively unreachable, except through less capable antennas that struggle to close the link at full data rate. Every day that Voyager 1 continues to transmit is a small victory against entropy. Every faint signal that arrives at Goldstone or Canberra or Madrid carries with it the latest measurement of a region of the universe that no other instrument can reach. The mission's continuation is not guaranteed. The power decreases by roughly 4 watts per year. The thrusters age. The memory chips are vulnerable to cosmic ray strikes. The mission will end, not with a decision to turn it off, but with a failure that cannot be fixed from 24 billion kilometers away. When Voyager 1 finally goes quiet, it will not be because someone pulls the plug. It will be because a thruster line freezes and the antenna drifts off Earth, or because the RTGs drop below the minimum power threshold, or because a component fails that has no workaround. The spacecraft will continue on its trajectory indefinitely, moving at 17 kilometers per second relative to the Sun, carrying its cargo through a galaxy that will receive it in silence. That cargo. We have not yet spoken about the golden record. Voyager 1 carries a 12-inch gold-plated copper disc, the golden record, containing 115 images encoded in analog format, greetings spoken in 55 human languages, a 12-minute compilation of natural sounds from Earth, and 90 minutes of music from cultures around the world. Carl Sagan chaired the committee that assembled its contents. The record includes instructions for playback, a stylus, and diagrams showing how to reconstruct the images from the encoded signals. It is, in the most literal sense, a message in a bottle cast into the cosmic ocean, an artifact of a civilization trying to announce its existence to whatever might, against all probability, find it. The record will never be found. The odds are functionally zero. The galaxy is so vast, and the spacecraft is so small, and the probability of any civilization being in the right place at the right time to intercept an object drifting at 17 kilometers per second through the interstellar medium is so vanishingly small that it can barely be calculated as a meaningful number. Carl Sagan knew this. The people who assembled the record knew this, and they included it anyway, not because they expected it to be found, but because the act of creating it said something true about the species that built Voyager, and about what it means to look outward into the dark and choose to reach. The Golden Record is a companion to science. It is the emotional and philosophical counterpart to the plasma wave data and the cosmic ray measurements and the magnetometer readings. The science says, here is what is out there at the edge of the sun's domain, and here is what we measured, and here is how complicated and beautiful and strange it turned out to be. The record says, and here is the species that built the machine that made those measurements, and here is what we sound like, and here is what we love. Both are messages sent outward into a space that, as far as we know, contains no one to receive them. Both are extraordinary acts of commitment to the idea that looking outward with instruments and with art is worth doing regardless of whether anyone is watching. Stand on a hilltop at night, far from any city, in a place where the sky comes all the way down to the horizon. The stars overhead are thick and cold and still. The Milky Way, if the night is dark enough, spreads across the sky in a soft, pale band, not bright enough to cast shadows, but bright enough to feel like something more than light. It is the interior view of our own galaxy, seen edge-on from deep inside one of its spiral arms, 30,000 light-years from the center. It has been there every night of your life. It was there before your parents were born, before their parents were born, before the first human beings looked up from a savanna and wondered what it was. Now hold that image in your mind and place, somewhere in that darkness, somewhere in a direction roughly toward the constellation Ophiuchus, a little above the plane of the galaxy, a single point of light so faint that no human eye could see it, even from the darkest desert on Earth. That point is Voyager 1. It is moving away from you at roughly 61,000 kilometers per hour, and it has been moving for nearly half a century, and the measurements it is sending back are arriving at Earth in signals weaker than 10 femtowatts, where femto is the prefix for 10 to the power of -15. Something in the human mind wants to make this comprehensible by scaling it. But the moment you try, the moment you convert the distances into walking times or driving times or the number of times you could circumnavigate the Earth, the numbers simply become different large numbers, and the intuition does not follow. Some things cannot be made small enough to fit inside ordinary experience. The distance to Voyager 1 is one of them. What you can do is hold the fact of it, the simple, unadorned fact that a machine the size of a small car built by human beings in the 1970s is now beyond the sun's protective bubble, drifting through the ancient gas of the galaxy and sending back measurements. That fact is comprehensible without being scaled. It sits cleanly in the mind as what it is, something our species did and continues to do, at extraordinary cost and with extraordinary patience. Stay with this for a moment, because the persistence of the mission, the 5 decades of engineering, maintenance, problem-solving, and attentive listening that have kept Voyager 1 transmitting, is not separate from the science. It is part of the same story. The persistent plasma hum that Stella Koch-Ocker identified in 2021 was detectable only because someone was still listening. If the mission had been terminated in 2000, or in 2010, or even in 2015, the hum would never have been found. The 2020 density anomaly, the unexplained elevation of plasma density and magnetic field that persists to this day, would never have been detected. Every year of the mission's continuation has been a year of new data from a place that no other instrument can reach, and that data has repeatedly surprised the scientists who received it. The persistent hum deserves one more pass of consideration, because its implications have not yet been fully absorbed by the scientific community. Before Ocker and her Cornell colleagues identified the continuous narrowband emission in 2021, the Voyager 1 plasma wave data produced a measurement of the interstellar plasma density roughly once every year or two, whenever a solar shock arrived and triggered the right conditions. The result was a sparse, episodic profile, a handful of data points spread across nearly a decade of travel, each one precise but isolated. The density gradient was visible in these points, but barely. You were essentially trying to fit a curve through a few isolated measurements and hoping the interpolation between them was meaningful. With the persistent hum, the situation changed fundamentally. The sampling became continuous, or nearly so. The density profile became a line rather than a scatter of dots. And the line revealed something that the sparse data had only hinted at. The density of the very local interstellar medium is not just increasing with distance from the heliopause in a smooth, predictable way. It fluctuates. It varies on scales of fractions of an astronomical unit, then smooths out over larger scales, then fluctuates again. This multi-scale structure is the signature of turbulence, real physical turbulence in the interstellar plasma, cascading energy from large scales down to small ones in a process that has been studied theoretically for decades, but never directly measured in the local interstellar medium before. The turbulence measurements from Voyager 1 are, in a sense, the first local ground truth for a process that astrophysicists rely on in model after model of galaxy formation, star formation, the propagation of cosmic rays through the galaxy, and the dynamics of the interstellar medium on large scales. The Kolmogorov turbulence spectrum, a theoretical description of how energy cascades from large eddies to small ones in turbulent fluids, developed by Soviet mathematician Andrei Kolmogorov in 1941, has been applied to the interstellar medium for decades on the assumption that the same cascade process that governs turbulence in rivers and in Earth's atmosphere also governs turbulence in the tenuous plasma between the stars. Voyager 1's measurements allow this assumption to be tested, at least locally, for the first time. Some analyses of the Voyager data suggest that the local interstellar turbulence spectrum is broadly consistent with the Kolmogorov description. Others find deviations that could indicate additional physical processes at work. The measurements are recent enough that the theoretical community has not yet fully processed them. And there is something philosophically striking about this. Kolmogorov developed his turbulence theory in Moscow in the middle of the Second World War as a contribution to pure mathematics applied to fluid dynamics, with no conceivable application to interstellar plasma in mind. The equations he wrote down described the statistical behavior of turbulent flows in ways that turned out to be broadly universal, applicable not just to water and air, but to plasmas, and, apparently, to the medium between the stars. Science is full of these connections, these unexpected arrivals of theory and territory its creators never imagined. But the connection between Kolmogorov's wartime equations and the plasma wave data from a spacecraft now drifting through interstellar space is one of the more poignant examples. It is a reminder that the universe, despite its staggering scale and its physical variety, has a tendency towards certain mathematical patterns that repeat across wildly different conditions and wildly different scales. This is worth pausing on, not as a transition to the next technical topic, but as an invitation to feel the weight of what it means. The same mathematical structure that describes turbulence in the air above your city, in the water swirling around a rock in a mountain stream, in the convective columns of gas on the sun's surface. That same structure appears, at least approximately, in the interstellar plasma through which Voyager 1 is moving, 24 billion kilometers from the Earth. The universe is not made of disconnected phenomena, each with its own special set of rules. It is made of a relatively small number of deep physical principles that express themselves differently at different scales and in different materials, but are, at bottom, the same principles. The interstellar medium, the ocean, and the atmosphere are all different faces of the same underlying mathematics. This is, in a way, the most fundamental thing Voyager 1 has confirmed, that our models are not completely wrong. That the universe we live in, as strange and vast and complex as it is the same universe from the inside of the heliosphere to the outside of it. The laws of physics do not change at the heliopause. Plasma behaves like plasma. Magnetic fields behave like magnetic fields. Turbulence behaves, at least approximately, like turbulence. The extrapolation that scientists had been making, taking what we know from measurements in the inner solar system and projecting it outward to the interstellar medium, was not wrong in its foundations, even if it was wrong in its details. That is a remarkable thing to be able to say, given how far the extrapolation had to reach. Now we arrive at the questions that the data cannot answer. And these are the most important questions of all. What is the 2020 anomaly, really? What crossed Voyager 1 that year? Or what did Voyager 1 cross that changed the plasma environment around it and has not changed back? This is not a question that admits a tidy answer. The data shows elevated density and elevated magnetic field strength persisting for years in a region of the very local interstellar medium that should, by the prior baseline, have been relatively quiet. 3 explanations have been offered: a denser interstellar cloud, a sustained solar pressure event, or an internal boundary within the VLISM. And none of them is clearly ruled out by the available evidence. Here is what makes this genuinely difficult. Voyager 1 is a single-point measurement. It is moving through a 3-dimensional medium at 17 kilometers per second. When it records a change, it cannot tell you whether the change is a spatial structure, a boundary between 2 physically distinct regions that it crossed, or a temporal change, something that happened to the region around it while it was there. A moving sensor in a changing medium cannot cleanly separate space from time. To determine whether the 2020 anomaly represents a new spatial region or a new temporal phase of the same region would require either multiple spacecraft at different locations, which we do not have, or a much more complete theoretical model of the VLISM structure than currently exists. What does the heliopause look like from the outside on scales larger than the 2 crossing points sampled by the Voyagers? We have 2 measurements: Voyager 1 at roughly 122 astronomical units in the direction of Ophiuchus, and Voyager 2 at roughly 120 astronomical units in the direction of Telescopium. 2 points on the surface of a 3-dimensional structure. From these 2 points, combined with the indirect Ibex and Cassini energetic neutral atom data, scientists can build a model of the heliopause's approximate shape and location. But the uncertainty in that model is enormous. The heliopause could be significantly closer in some directions and significantly farther in others, and we simply do not have the measurements to know. Does the bow shock exist? This question is still genuinely open. The Ibex velocity measurements suggested the heliosphere might be moving too slowly to generate a true bow shock. Some models say yes, there is one, just weaker and farther out than previously thought. Other models say no. The 2 Voyager spacecraft, moving in their respective directions, have not yet traveled far enough from the heliopause to encounter a bow shock if one exists, and their instruments may not be the ideal ones to detect it when and if they do. We cannot know from the current data whether there is a shock wave standing in the interstellar medium ahead of the heliosphere's motion, or whether the heliosphere is moving through the galaxy subsonically, like a slow ship through calm water. What exactly are anomalous cosmic rays accelerating to, and where? The data from both Voyager 1 and Voyager 2 has raised questions about the relative importance of the termination shock, the heliosheath, and the heliopause as acceleration sites, but has not resolved them. A definitive answer would require measurements of the full particle energy spectrum at multiple locations simultaneously, at the termination shock, throughout the heliosheath, and at the heliopause, which is not currently possible with any existing mission. Where does the very local interstellar medium end and a different region of the local interstellar cloud begin? The density gradient that Voyager 1 has been measuring, steadily increasing electron density with distance from the heliopause, implies a structure in the VLISM. But what kind of structure? A smooth gradient across the entire local interstellar cloud? A nested series of substructures within it? A distinct boundary between the local interstellar cloud and a neighboring cloud? The data so far does not resolve this, and will not for as long as Voyager 1 is the only measurement point. And behind all of these specific questions, there is a question of deeper uncertainty that cannot even be approached with current data. We do not know what the interstellar medium looks like beyond the very local region Voyager 1 is sampling. The VLISM is a tiny, tiny fraction of the galaxy's interstellar medium. Voyager 1 has traveled, since crossing the heliopause, roughly 30 astronomical units into interstellar space. 1 astronomical unit is roughly 150 million kilometers. 30 astronomical units is roughly 4.5 billion kilometers. The nearest star to the Sun, Proxima Centauri, is about 268,000 astronomical units away. Voyager 1 has crossed 30 of those 268,000 astronomical units, a little more than 1/100th of 1% of the distance to the nearest star. Whatever the interstellar medium looks like at larger scales, at the scale of parsecs, of hundreds of light years, of the full extent of the local bubble and beyond, we cannot know from Voyager 1's measurements. We infer it from remote observations, from pulsar dispersion measures, from the absorption of starlight, from radio observations of hydrogen and other species. But we do not know it from direct measurement. There is something profound in that limitation. We have sent a spacecraft to the edge of the solar system and into interstellar space, and what it has revealed is how much of interstellar space remains entirely beyond our direct reach. The 30 astronomical units of the VLISM that Voyager 1 has sampled are, in the context of the galaxy, not even a rounding error. They are an infinitesimal scratch on the surface of an inconceivably vast ocean. And the scratch has revealed more complexity, more structure, more turbulence, and more mystery than anyone expected. What lies deeper? What the ocean is truly like on the scales that matter for understanding the galaxy? We cannot know. Not yet. Possibly not ever, with any instrument we are currently capable of building and launching. What kind of universe do we live in, if even this extraordinary achievement, sending a machine beyond the sun's protective bubble and listening to it describe what it finds, reveals more questions than it answers? What kind of universe is it that hides its deepest truths, not behind simple barriers that can be crossed, but behind layers of complexity that deepen with every measurement? What does it say about us, the species that built this machine, that has been listening to it for nearly 5 decades, that spent months decoding garbled computer signals from 24 billion kilometers away and patching a computer with 69 kilobytes of memory, that we keep listening, keep decoding, keep sending commands across the void, regardless of whether the answers we receive confirm what we hoped or complicate what we thought we knew? Is there a bowshock out there, standing in the interstellar medium ahead of our sun? And if there is, what does it look like from the outside? Has any living thing on any planet orbiting any star ever seen the bowshock of another stellar system from the interstellar medium? We cannot know whether such things are even possible to observe. What is Voyager 1 moving through right now, in this moment, as you listen to these words? What density fluctuation is the plasma wave subsystem registering? What magnetic field line is the magnetometer tracking? The data will not arrive for 22 hours. Whatever Voyager 1 is experiencing right now, in real time, is inaccessible to us for nearly a day. Is the 2020 anomaly a cloud boundary? Is it a sustained solar pressure event? Is it something else entirely? Something that has no name yet because it has never been seen before? We cannot know. The instruments that would most cleanly distinguish between these possibilities, a working plasma spectrometer, a functioning charged particle instrument, have either failed or been shut down to conserve power. The mission continues with what it has, and what it has is the plasma wave subsystem and the magnetometer, measuring 2 quantities in a region where 4 or 5 would be necessary for certainty. Could the heliosphere right now be smaller than it was 10 years ago? Could a change in the solar cycle, or a change in the density of the interstellar medium the solar system is passing through, have compressed the heliopause inward? Probably not by much. The response time of the heliosphere to external pressure changes is long, but we cannot rule it out, and we have no way to measure the heliopause from the inside with the fidelity needed to detect a small change in its position. What will Voyager 1 find as it continues? Will the density keep rising? Will the magnetic field keep increasing? Will the anomaly that began in 2020 resolve into something recognizable? Or will it persist and deepen, suggesting that the spacecraft has entered a fundamentally different region of the local interstellar medium that extends for tens of astronomical units ahead of it? We cannot know. This is not the comfortable, we do not know yet, but we will find out. This is the deeper admission. Some of what Voyager 1 is discovering may never be fully interpretable, because the measurement constraints imposed by a single aging spacecraft on a single trajectory through a 3-dimensional, time-varying medium are irreducible. The answers it can provide are constrained not just by the limits of our instruments, but by the fundamental geometry of the situation. One point in space, moving in one direction, at one moment in the solar cycle, through a medium that varies in all 3 dimensions and through time. The data is real and precious, and it is permanently, irreducibly incomplete. There is a particular kind of scientific humility that the Voyager mission has imposed on heliospheric physics, not the ordinary humility of incomplete data that future measurements will remedy, but something deeper. Something closer to the recognition that the universe is under no obligation to be fully knowable from the inside of a single planetary system, with a single set of instruments at a single moment in the history of a single star. The heliosphere is our home. The heliosphere is where all of human history has taken place. Every war and every scientific discovery and every work of art and every life, without exception, in an environment shaped and protected by the sun's magnetic bubble. And that bubble, it turns out, has an edge that is turbulent and porous and fluctuating and full of surprises, pressed against a galactic medium that is itself structured and turbulent and denser than expected, in a local environment that is historically contingent and will eventually change. And the one machine we have sent to look at this edge directly is running out of power piece by piece, year by year, and will fall silent within the next decade, leaving behind a picture that is richer than anything the pre-Voyager models imagined, and less complete than the questions it has opened require. That is the picture. That is what Voyager 1 has found at the edge of our solar system, and what it is still finding, and what it will continue finding until it can no longer speak. Once you see that picture in full, not just the technical details of the termination shock crossing or the plasma wave measurements, but the whole arc of what this mission has meant and what it has revealed, the entire story of the solar system and its place in the galaxy looks different. It inverts. The heliosphere is not a static container inside which the solar system sits. It is a dynamic, breathing, historically contingent structure, inflated and deflated by the sun, shaped and compressed by the surrounding galaxy, fluctuating with the sun's activity cycle, and with the varying density of whatever interstellar medium the solar system happens to be passing through. It has been larger in the past. It will be smaller in the future, perhaps much smaller, if the solar system enters a denser cloud. The cosmic ray environment of the inner solar system, the radiation environment in which life has evolved on Earth, has not been constant. It has varied and will vary again on timescales that are long by human standards, but short by geological ones. The boundary is not passive. It is the site of some of the most complex plasma physics in the heliosphere: shock acceleration, magnetic reconnection, turbulent cascade, the mixing of two fundamentally different magnetized plasma domains. It is where the sun's influence ends and the galaxy's influence begins. And that transition is not clean or sharp, but gradual and dynamic, and full of physics that is not yet fully understood. And at the very center of all of this, at the center of the heliosphere, orbiting the sun at a distance that is a tiny fraction of the bubble's radius, living beneath an atmosphere and a magnetosphere and the bubble itself, protected by layers of physics from the full intensity of the galactic cosmic ray flux, is a small blue planet, remarkable in its complexity and its fragility, whose most distant mechanical emissary is currently drifting through the interstellar medium 24 billion kilometers away, sending back faint signals about the nature of the place where the sun ends and the galaxy begins. The perspective shift is not comfortable. It does not resolve into simplicity. The comfortable version, solar system here, space there, Voyager crossing the boundary and proving that we can reach it, is real. But it is the surface of something much deeper and stranger. The deeper version is a boundary that moves, a medium that fluctuates, a measurement that is always partial, and a universe that deepens rather than simplifies under every instrument we point at it. This is where the meditation on what Voyager 1 has found arrives, finally, at the question of what it means to be here, inside this bubble, looking outward. There is a human habit of imagining that the most important boundaries are the ones we can see. The shoreline where the land meets the ocean, the tree line where the forest ends and the alpine rock begins, the horizon where the earth seems to meet the sky. These are the boundaries that shaped the first maps, that gave early navigators their reference points, that organized human geography into zones of the known and the unknown. The boundary of the heliosphere is not visible. It cannot be photographed. It does not have a color or a texture or a sound that the human ear could register. It exists only in measurements, in the frequency of electron oscillations detected by a plasma wave instrument, in the direction of a magnetometer needle, in the count rate of a particle detector. And yet, it is, in a meaningful sense, the most important boundary in our immediate cosmic neighborhood. It is the edge of the space the sun has carved out and maintained, the outer wall of the only home our species has ever known. Voyager 1 has been, for nearly 5 decades, our one set of eyes on that boundary from the outside. Everything we have learned about it from direct measurement has come through instruments that were designed before the space shuttle flew, that have survived conditions no engineer could fully have anticipated, that have been nursed and coaxed and patched by teams of dedicated scientists and engineers across more than 4 decades of working life. The mission has outlasted the careers of the people who built it. It has outlasted the institutional memory of many of the early design decisions. There are engineers working on Voyager today who were not yet born when it launched. What they have inherited is a set of data that has rewritten the boundary conditions of heliospheric science. Not just refined the old picture, genuinely rewritten it in ways that matter for how we understand the sun's place in the galaxy. The termination shock is real, but it is not where the anomalous cosmic ray acceleration peaks. The heliosheath is turbulent and magnetically structured, not a simple zone of compressed wind. The heliopause is porous and dynamically active, not a clean wall. The interstellar medium immediately beyond is denser than expected, turbulent on all observable scales, magnetically aligned in unexpected ways, and currently exhibiting an anomaly whose cause remains genuinely unknown. The heliosphere's shape is more complex than the comet model predicted. The bow shock may not exist. And threaded through all of these findings is a persistent hum, a faint, continuous emission from the interstellar plasma itself, first heard by Stella Koch-Ocker and her colleagues in 2021, that has transformed a mission of episodic measurements into something approaching a continuous map of the edge of the sun's domain. This is what Voyager 1 detected at the edge of our solar system. Not one thing, but a layered sequence of surprises, each one replacing a simple picture with a complex one, each one asking more questions than it answered. The wall turned out to be a coast. The coast turned out to be a turbulent and living boundary. And the ocean beyond it turned out to be deeper, stranger, and more structured than anyone had imagined from the inside. There is a long human tradition of what happens when explorers return from a boundary that was previously only theoretical, when the map that said "here there be dragons" is replaced by a map that says "here there be something stranger than dragons and more real." It happened when Magellan's expedition returned from the first circumnavigation of the Earth, and the flat conceptual geography of the medieval world gave way to the curved, finite, navigable globe. It happened when the Apollo astronauts returned from the Moon and the photographs they brought back. The Earthrise photograph taken by William Anders in December 1968, the blue marble photograph taken in December 1972, changed forever the image a species had of its own home. The view from outside, it turns out, always changes the view from inside. You cannot see your home clearly until you have stood somewhere outside it and looked back. Voyager 1 has not sent back a photograph of the heliosphere. Its cameras stopped working decades ago, and in any case, the heliosphere is not the kind of thing that can be photographed in visible light. It is a magnetic and plasma structure, invisible to ordinary eyes. But the data it has sent back is, in a different sense, a view from outside. It is the first direct measurement of the space beyond the sun's domain, taken by an instrument that actually crossed the boundary, that actually sat in the interstellar medium and registered what it found there. And what it found is a picture of the heliosphere as a finite, historically contingent, dynamically active bubble in a galaxy that is vastly older and vastly larger than the bubble itself. The Sun is roughly 4.6 billion years old. The galaxy it inhabits is roughly 13.6 billion years old, 3 times the age of the Sun, old enough that the first generation of stars lived and died and exploded before the Sun's molecular cloud had even begun to collapse. The local bubble, inside which the solar system currently sits, was carved out by supernovae that occurred in the last 10 to 20 million years, a recent event in galactic terms, a moment ago. The Sun has been inside the local interstellar cloud for somewhere between 40,000 and 150,000 years, a geological eye blink, shorter than the span of anatomically modern human existence on Earth. Before the local interstellar cloud, the solar system passed through different regions of the interstellar medium, some perhaps denser, some perhaps more magnetically complex, some perhaps capable of compressing the heliosphere inward by significant amounts. The heliosphere as it exists today, the heliosphere that Voyager 1 has spent 47 years crossing and has now departed, is not eternal. It is a current configuration. It is the product of this Sun, at this moment in its life, passing through this particular region of this particular galaxy at this particular time. It will be different in 10,000 years, and very different in 1,000,000, and essentially unrecognizable, from a heliospheric physics standpoint, in 100 million. The stars the solar system will pass near in its future galactic orbit have not yet been identified. The interstellar clouds it will pass through are not yet mapped. The future of the heliosphere is, in the most literal sense, unknown. And the past. The past is written partially in the geological record of the Earth, in the iron-60 deposits from nearby supernovae, in the variations in cosmogenic isotopes that suggest periods of higher cosmic ray flux, in the evolutionary transitions that some researchers tentatively connect to changes in the galactic environment of the solar system. The Earth has been inside this bubble for most of its biological history, protected to varying degrees from the full galactic cosmic ray flux, shaped in ways that we are only beginning to understand by the properties of the space surrounding the solar system. Life on Earth is not just a product of the Sun and the planet. It is, in some sense, partial, contingent, not fully characterized but not negligible, a product of the heliosphere, and of the heliosphere's history, and of the galactic environment that has shaped that history. There is a thought that arrives here quietly, without fanfare, but with the full weight of the evidence behind it. The creatures that built Voyager 1, the ones who designed its instruments and calculated its trajectory and assembled its structure in a clean room in Pasadena, California, in the mid-1970s, are creatures whose evolution took place inside the heliosphere's protection. The cosmic ray flux that reached their ancestors over hundreds of millions of years of evolution was the modulated flux of the inner solar system, reduced and filtered by the Sun's magnetic bubble. The mutations that drove the evolution of the lineage that eventually produced human beings were, in part, set by the cosmic ray environment inside the heliosphere. The heliosphere did not create life, but it shaped the radiation environment in which life evolved. The boundary that Voyager 1 crossed in 2012 is, in a very real sense, the outer wall of the environment that made us. And we sent a machine through it, and the machine is still transmitting. The time may be drawing short. The low-energy charged particles experiment was turned off in April 2026 to conserve power. As of this moment, only the plasma wave subsystem and the magnetometer remain operational. The plutonium generators lose roughly 4 watts per year. Sometime in the early 2030s, the power may fall below the threshold needed to operate even these last 2 instruments. Sometime after that, perhaps in the mid-2030s, perhaps a little later, the transmitter itself may fall silent, and the long conversation between Earth and its most distant emissary will end. When it does, the silence will be absolute and permanent. There will be no replacement, not soon. The scientific community has been advocating for an interstellar probe mission, a purpose-built spacecraft aimed at the heliosphere's boundary, using advanced propulsion to arrive in decades rather than half a century. But as of today, no such mission has been funded or approved. The gap between the end of Voyager's scientific life and the beginning of any successor mission could be 10 years, or 20, or more. During that gap, the very local interstellar medium will be observed only remotely from the inside of the heliosphere through the indirect techniques of energetic neutral atom imaging and radio observations and theoretical inference. The direct measurement will be gone. This is not a tragedy in the ordinary sense. It is simply the reality of what it costs to explore the outer boundary of the solar system. The time, the money, the political will, the engineering patience. The Voyager missions were, by any measure, among the most scientifically productive missions in the history of space exploration. They were also, in some ways, accidents of opportunity, made possible by a planetary alignment that occurs once every 175 years, funded in an era of scientific optimism and Cold War competition, launched by a generation of engineers who built things to last because they had no other choice. The conditions that produced Voyager do not repeat automatically. They have to be recreated deliberately through institutional commitment and public investment. What Voyager has given us, and what it continues to give, with every faint signal arriving at the Deep Space Network antennas, is irreplaceable. Not just the data, though the data is extraordinary, but the knowledge that it is possible. The knowledge that a machine built by human beings can travel to the edge of the sun's domain and report back on what it finds there. The knowledge that the boundary is real, that it is crossable, that the interstellar medium is measurable, that the universe beyond the heliosphere follows the same laws as the universe within it. These are not small things to know. They are, in some ways, the most important things the species has learned about its cosmic address. The heliosphere is our bubble. It is the sun's gift to its planetary system, a region of reduced cosmic ray flux and relatively stable magnetic environment maintained by the continuous outflow of the solar wind, pressing outward against the surrounding galaxy. It is not eternal, not permanent, not invulnerable, but it is here now, and it has been here for the entire history of life on Earth, and everything that has ever lived on this planet has lived within it. Voyager 1 is the one object we have ever sent beyond it. It is moving away right now at 17 kilometers per second, deeper into the galaxy's ancient plasma, measuring the hum of the interstellar medium with 2 instruments that are still working against all probability. The signal it is sending back takes 22 hours to arrive. The signal we send in reply takes another 22 hours to reach it. Every exchange is a 2-day conversation across 24 billion kilometers of space, conducted in radio waves weaker than a refrigerator light, received by the most sensitive antennas our civilization has built. And we are still listening. There is something in that, in the act of still listening after 5 decades, across a distance that makes the word distance seem inadequate. That says something true about what science is at its best. Not just measurement, not just data collection, not just the accumulation of facts about the universe, but the commitment to keep attending, to stay present to the signal even when it gets fainter, to resist the temptation to declare the work finished when the work is demonstrably not finished. The universe has not run out of things to show us at the edge of the solar system. It has, if anything, revealed that there are more things to see there than anyone imagined. The simple story, solar wind, boundary, interstellar space, has given way to a story of nested surprises, each layer more complex than the last, each answer opening onto several more questions. The wall that Voyager found is not a wall. It is a coast where the sun's domain meets the galaxy. The coast is turbulent and porous and magnetically active and denser than expected and humming with the thermal noise of interstellar electrons. And beyond the coast, there is an ocean, the interstellar medium, the space between the stars, the vast cold gas of the galaxy, that Voyager has barely touched and that stretches away in all directions for distances that reduce the 47 years of the mission to a single short step. That ocean is where we live, in the larger sense. Not on the coast, not at the heliopause, but inside the bubble, on a small rocky planet looking outward. And the outward look, extended as far as one machine can extend it, has shown us that the edge of our home is stranger and more beautiful and more uncertain than we knew. If this changed how you think about the solar system's edge and about the small machine that crossed it and kept going, then the time was well spent. Thank you for staying.